All right, so we're off and running. So what we did already, we've already seen the we've already done the speed run for the exam, but I do want to just mention a couple of things about what to do with your particular exam score. Now that we've taken it up, hopefully it's making more sense to you. But definitely make sure that you understand exactly what happened on exam number 1 before you let yourself move on. So basically, typically what I do in this class is I'll throw the exam scores up on here in a frequency distribution, just kind of let you see how you're doing within the class. We don't have enough students in this class to get a nice sample of that, so this is from a previous class. And basically, this is sort of typical of the performance in this exam. So if you are in this category over here, definitely just keep doing what you're doing. Keep doing your pre-test, your post-test, your study plans, all that work that you've been doing. Basically, you either got a perfect or it was some slip of the finger that might have cost you a couple of grades. If you're down here, this is typically when you got like one question wrong. So maybe you didn't unpack the frequency distribution graphs correctly. Make sure that you know what happened there, what the error was. But basically this is typical of one question was missed. So definitely make sure that you know what happened on that question, how to do that question before moving on. You know, go back to the lecture notes, come see me in the office hour. And then basically, if you're down here, then we need to change something about what's going on in this course. So this is not just 1 or 2 mistakes. This is indication that something is just not transferring and stuff is not making sense. So if that's you, a couple of things to keep in mind. Number 1, you can still turn it around. This can still be your lowest exam, and if you go to the syllabus, you'll see that that is graded on a sliding scale, so you won't be, your grade won't be impacted too much, but definitely use it as the wake-up call that it is, and something needs to change, whether it's doing more of the study plan, making sure that you get all of the pre-tests, all of the post-tests, and all the homework done, whatever it is, something needs to change in that regard. So make sure that you are taking the steps that are required in order to do that. Because we have in this accelerated summer course, exam number 2 is coming up in just a little bit. So we actually have exam number 2 coming up next time we meet. So that is coming up on the 5th. And once again, it'll be at 10 a.m. It'll be in the 2nd hour. And it will once again be a computational exam. So it will look very much like exam number 1. We're actually going to go through a Excel demo today that will mimic what half of your exam is going to look like. So it's going to be another Excel exam. It'll be 8-ish questions. I'm still finalizing it. And once again, it'll be open book, which means open everything except communications with other people. So especially for the hypothesis testing that we're going to be doing on that exam, make sure that you are ready to go with the 5 steps. Make sure that you're ready to go with step 5, knowing whether to accept or reject that null hypothesis. Basically, whatever materials you need in order to do this exam, is not going to be any sort of surprise in terms of what you're going to see. We're going to see a probability question. We're going to test your ability to read frequency distribution, specifically the normal distribution. You're going to be calculating percentages when you start with a raw score using the unit normal distribution. You're going to be calculating raw scores when you start with a percentage using the unit normal distribution. And you're going to be doing hypothesis tests. So everything that we've been working on is what's going to be on the exam. There won't be any surprises. So make sure that if you need additional resources to get any of those types of questions done, that you have them ready to go for exam number 2. And then as before, we're going to have a review session for exam number 2. This is going to be an open review session. It's going to happen in the first hour of Wednesday's class, so at 9 a.m. We're going to have the open review session. This is going to be completely student driven, so if you have any questions, if you want to see anything once more, this is the time to come in and ask about that. But I also realize that some of you might want to prepare in different ways, so it is completely optional. Feel free to show up at 9 a.m. for the review. I will be here ready to go. If not, make sure that you're here by 10 a.m. for the beginning of the exam. All right, so any questions on exam number 2? Mm-hmm.
Is it only up to chapter 5, or does it also include chapter 6?
It is only up to chapter 5.
Okay.
So we got chapter 4 and we got chapter 5. Mm-hmm. All right, any other questions on the exam? Okay, so what we're going to do today we're going to wrap up chapter 5. We're going to wrap up what we need to know for exam number 2. And again, we are developing the skills right now that allow us as psychologists to intelligently, unbiasedly, I guess, if that's a word, go from a sample to a population. And the importance of that cannot be understated, because without statistics, that move of generalizing from a sample to a population can become so full of biases and just obscure any of the truth. So you've learned in other psychology courses that we have what's known as a confirmation bias. It's one of the things that we tend to, the way our cognition works, we tend to seek out confirmatory evidence for whatever we think should be the case, whatever we believe should be the truth. And that happens a lot of times going from samples to a general population. So for example, you could take a look at the exact same data, and you'll see people do this all the time. You can take a look at the exact same data, and one scientist who's really hoping that this treatment works might take a look at this sample and say, you know what a successful experiment, what a successful treatment. Look how big the difference is in their learning outcomes. We got to spread this out to the entire population. We got to generalize this to the entire population. Another scientist, another psychologist who has an opposing view, who has an alternative theory that they want to bring to the population, might take a look at the same data and say that difference isn't too big. Those learning outcomes are barely any bigger than we would have expected without this treatment. We should definitely not promote this or generalize it to the population. So we got two people on two different sides of this argument looking at the same data and interpreting it in a way that they want to believe it should be. Statistics takes that out. Statistics takes the data, puts it into the hypothesis testing procedure, and out comes the truth. So once again, we need this as human beings if we're going to get to the truth of what's going on in psychology. And right now, again, as we saw before, is where all that work that we've been doing is going to pay off. All of that becoming very familiar with means and standard deviations and z-scores and how to use z-scores and practicing so that it becomes very, very, very automatic. That's going to be put into play right now when we finally get to the actual sort of real business of and real power of statistics, which is to take a look at psychology data from real psychology situations and make decisions about whether we should generalize to the population or we shouldn't generalize to the population. And much like I mentioned the metaphor of the statistician is like the ninja, the one that can get the job done, we do have a 5-step procedure for hypothesis testing. And much like this graph of ninja training and recruitment, the 5-step procedure for that, we are working our way there. So we want to get you to the point where you will be completely ready to do this 5-step testing procedure all on your own. However, you are not quite there yet. So right now, you can do certain parts of this 5-step procedure alone. So right now, you can do step 4 all by yourself. You can calculate your sample's z-score on the distribution. You can do step 5 all by yourself. You can see where your sample z-score is compared to your cutoff score and decide, do I accept or reject the null hypothesis. You're very close to being able to do step 1 all by yourself. You got half of it right now. Today we're going to complete the other half. Step 2, where you figure out your comparison distribution. We do not have that quite yet. And step 3, where you look up your cutoff scores. We don't have that yet either. So we're missing pieces in order to give you the complete skills required. So today we're going to work on that, and we are going to give you the skills that you need to do step 1 all by yourself. And once we get those done, you'll be ready to learn the skills so that you can do step 3 all by yourself, find those cutoff scores, those lines in the sand. And then chapter 6, after exam 2, is where we're going to get step 2 and get the complete package. All right, so what are we going to do today? We're going to take a look at one-tailed versus two-tailed hypothesis tests. We're going to do some hypothesis testing in class demos. We're going to take a look at that self-esteem experiment one more time, and then you'll have time in class to practice on car crash, a study about car crashes, a study about timeout penalties as well. And all of these 3 demos are going to be almost exactly like what you're going to see in the exam. So the setup of it is going to be the same, so it's going to be good practice for what is coming up on exam number 2. All right, so the hypothesis testing procedure. So once again, we got that 5-step procedure. Step number 1, restating that question that we're interested in as a research hypothesis and a null hypothesis about the population. Step 2, determine the characteristics of the comparison distribution. Step 3, determine the cutoff sample score on your comparison distribution. That's your line in the sand. Step 4, determine your sample score on the comparison distribution. That's where your sample actually is. And then finally, step 5, decide whether you're going to accept or reject that null hypothesis. So we have been kind of skirting around the issue of one-tailed and two-tailed hypothesis tests. There's actually 2 basic different types of hypothesis tests, and they all have to do with the kind of question that you're asking. And the places that it impacts your procedure the most is going to be in steps 1, and it's going to be in step 3. So we got to introduce this idea of the hypothesis, two-tailed versus one-tailed, so that you can do steps 1 and 3, that is required knowledge for that. All right, so what's a one-tailed versus a two-tailed hypothesis test? These are hypothesis tests that are based on the type of question that you're asking. So two-tailed hypothesis tests, they're called two-tailed because of the nature of the question. You're going to end up with 2 lines in the sand. 1 line for a decrease, 1 line for an increase, right? That's for a two-tailed test, and that's why it's called two tails. 2 lines in the sand. You got 2 tails to your comparison distribution, 1 body, 2 tails. On the other hand, some questions require a one-tailed hypothesis test. And in a one-tailed hypothesis test, you only have, as the it's the name on the tin says, you only have the one tail. So you only have one side, one direction that you're looking for an effect in. And that's why a two-tailed hypothesis test is called a non-directional hypothesis. And a non-directional hypothesis is when you're just wondering if your treatment has an effect, and you have no good reason to suspect that it might go one way or the other way. So a good example that we've already seen of a non-directional hypothesis test or a two-tailed hypothesis test, was Harlow's study on monkey attachment. So there was no reason before Harlow did his experiment to believe or to expect that the baby monkeys would go to one mother versus the other. Because you could say, well, the terry cloth mother, she's soft, she's cuddly, she offers, security and a tactile sensation. Those are good reasons why the monkey would prefer the terry cloth mother. On the other hand, the wire mesh mother gives food, it gives life, it gives sustenance. Those are good reasons why I should prefer the wire mesh mother. Which way is it going to go? We don't know. We have no reason to expect one way or the other. We're not interested in one way or the other. We just want to know, does the treatment have an effect? Is there a difference? So do they prefer the wire mesh mother? If so, interesting. Do they prefer the terry cloth mother? If so, interesting. We're just looking to see, does it have an effect? Another example would be people looking at the effects of social media on self-esteem. Maybe social media is bad for self-esteem because you get to see people at their best. You're always comparing yourself with people at their best, whereas you see where all the nuts and bolts of your own day are. So by social comparison, maybe it's bad for self-esteem. On the other hand, maybe it's good for self-esteem because you got a network and a community that you can belong to, that you can find people out there that are like you, share common interests, get into your own echo chamber, as it might be, and increase your self-esteem. So, good reasons to believe self-esteem might go up because of social media, self-esteem might go down because of social media. If we did an experiment, we would want to have a two-tailed hypothesis because we have no idea which way we might go. On the other hand, some questions are directional. Some questions have a specific direction that we believe they're going to go in. In that case, we want a directional hypothesis. So this is either when we believe they're going to go in a certain direction, or we only want them to go in a certain direction. So for example, we might say the treatment causes an increase. That might be the question we're asking. Does this treatment cause an increase? So does a particular treatment cause an increase in self-esteem? Right? Does a particular treatment cause an increase in people's ability to navigate a room? Right? Does a particular treatment cause an increase in the likelihood that women are going to ask for raises on the job? Right? Does a treatment increase something, make it more, add to it? These are all directional hypotheses because we're only interested in the one side. We're only interested in the one direction. So for a two-tailed hypothesis, you're always going in both directions. For a one-tailed hypothesis, sometimes you're interested in an increase. Does my treatment increase self-esteem? Does my treatment increase learning outcomes? Sometimes you're interested in a decrease, right? Does my treatment decrease depression? Does my treatment decrease anxiety disorders, right? Does my treatment decrease certain things? So in that case, you would want to have this side of your distribution, your comparison distribution, have the tail. So the tail is always on the side, the line in the sand is always on the side that you're interested in. If you're interested in a decrease, you pop it all onto that side. If you're interested in an increase, you put it all on the positive side. So far, so good? All right. And it's important to know whether you're doing a one-tailed hypothesis or a two-tailed hypothesis, because that is what is going to determine, going the wrong way. That is what's going to determine where your lines in the sand are. So those cutoff scores, those cutoff z-scores, they change depending upon whether you're doing a two-tailed test or whether you're doing a one-tailed test. So for a two-tailed test, they're in a certain position on positive and negative sides. For a one-tailed test, they're in a certain position either on the negative side or on the positive side. And the key thing here in determining your lines in the sand is that your tails, your tails always equals your alpha level. So you have to make your tails big enough so that they always equal your alpha level. And that's why it's important to know whether you have two tails or whether you have one tail. If you have one tail, you take your alpha level, let's say that it's 0.05, and you make this line, you draw this line in the sand so that this tail is 5% of the distribution. You figure out what z-score you need to put 5% into the bottom tail of this distribution. On the other hand, for a two-tailed test, you got to figure out which lines in the sand will put 5% into the tails in total. So half of it in here and half of it in here, you got to find that line in the sand. So if we were doing sorry about that. So when we do this, in order to find those lines in the sand, I was giving it to you before, now we're going to learn how to actually do it. In order to find those lines in the sand, you go to your unit distribution, normal distribution table. You go to that table that we've been using in Appendix A1, and you need to find whatever percentage in the tail you're looking for, and then find the z-score that's associated with that percentage. So let's take a look at a couple of those examples there. So let's say that we had, we'll start off with the classic 5% in the tail. We have an alpha level of 0.05, an alpha level of 5%. All right, so alpha level of 0.05, that equals 5% in the tail. So we want 5% in the tail. And let's say that we're doing a one-tailed hypothesis. We want all 5% to be placed in one tail. We need your tails to equal alpha. This has to be 5%. So we go to the unit normal distribution table, and we scan the percentages in the tail. So this column right here, which is the percentages in the tail, we scan that until we find something that's close to 5%. What's the closest one to 5%? There are actually two here that are equally close. There's 505 and there's 495. On the exam, you can use either of those. In your homework, I think you can use either. Try one. If it doesn't work out, try the other. But once we find a percentage in the tail, we then go across to find our cutoff score, to find that z-score. So that line in the sand that's going to put 5% in the tail for a one-tailed hypothesis test is 1.64. And then the last thing you need to do for a one-tailed test, if it's on the negative side like this is, that's minus 1.64. If it's on the positive side, that's positive 1.64. So you'll only find positive values in your table. Just remember it's symmetrical, and if you're looking for a decrease, does the treatment cause a decrease? Are symptoms reduced? Did the amount go down? Was there less after the treatment? If the language or the question is asking you for a decrease, make sure that your cutoff score is negative. If it's asking you for an increase, did scores improve? Did scores go up? Was there an increase in scores? Make sure that you have a positive cutoff score indicating an increase. All right, so that was for the two-tailed. What about, for the one-tailed. What about for the two-tailed? Well, for the two-tailed, you got to make sure that you take your 5% in this case, and you got to split it up into 2.5 in one tail, and 2.5 in the other tail. So you got two tails. Each of them has 2.5. Together, it equals 5%. All right, so make sure that your tails together always add up to your alpha level. So in this case, if we're doing 5% in the tails, and we got two of them, we know that we're looking for 2.5% in the tail. We scroll down our percentage in the tail until we find something that is close to 2.5%. As it turns out, we have exactly 2.5%. In our column there. We look across to see the z-score associated with that, and it is 1.96. So that's how you look up your cutoff scores for your two-tailed test. You got to split that alpha into two, and then get that find that z-score. And when you're reporting this for your cutoff scores, you need to report the negative side and the positive side. So you need to say, oh, it's minus 1.96 and positive 1.96. So that's going to be the case for your homework. For the exam, for a two-tailed test, I'm going to assume you mean both tails. So don't worry about putting the minus and the positives in the exam. Before your homework, just be aware that you need to put in the minus side of a two-tailed and the positive side of a two-tailed as well. All right, any questions so far on looking up your cutoff scores, looking up that part 3 of the hypothesis test? All right, so let's take a look at one more common alpha level, which is an alpha level of 0.01. So an alpha level of 0.01, that translates into 1% in your tails. So if we're doing a one-tailed hypothesis with an alpha level of 0.01, we take that alpha level and we put it all into one tail. So we need to find what z-score is going to give us 1% in the tails. So we take a look here for 1% in the tail. The closest is right there, 0.99. So we don't have exactly 1.0, but we got 0.99. That's 1% in the tail, as close as we're going to get. We see the z-score associated with that. And our cutoff score for a 1% alpha level for a one-tailed test is 2.33. If it's on the negative side, like this one, it's looking for a decrease, minus 2.33. If it was looking for an increase, positive 2.33. All right, and then if we were doing a two-tailed test, make sure that you are taking your alpha and you are splitting it into two and putting equal amounts on both sides. So in this case, we have 1% that is getting split into two. So that is 0.5% on one side, 0.5% on the other side. We go to our unit normal distribution table. We look up 0.5%. Once again, we have two values that are equally close to 0.5%. For the exam, you can use either one. For the homework, try one, and if it doesn't work, try the other. But importantly, we find 0.5% in the tail, find the z-score associated with it, and the cutoff score for a two-tailed test with an alpha of 0.1 will be minus 2.57 and positive 2.57. All right, so you now know how to do step 3. So determine the cutoff sample score on the comparison distribution of which the null hypothesis should be rejected. You first determine, is it a one-tailed or a two-tailed hypothesis test? You next determine what's the alpha level. If it's a one-tailed, you put it all into one side of the distribution and find the cutoff score that is associated with that percentage in the tail. If it's a two-tailed test, you take your alpha, you split it into two, and you find the cutoff score that is associated with half of that alpha percentage in each tail. All right, so that's for step 3. Let's take a look at what step 1 is, and then we'll save the demos for after a break. We've been going for about an hour because of the exam. But let's take a look at how to do step number 1, and then we'll take a break. All right, so step number 1, restate the question as a research hypothesis and a null hypothesis about the population. So far, we have been only doing two-tailed hypotheses for step number 1. All right, so the ones that we've been practicing so far, that's a two-tailed hypothesis, because we have only ever been asking, is there a difference between the treated population and the known population? So we have never asked so far, is there an increase or is there a decrease? We've just been asking, is there a difference between the two treatments? Did the treatment have an effect? Right? It's almost like you're taking a mystery drug and you don't know if it's going to make you better or if it's going to make you worse. So it might have an effect. We don't know if it's going to go one way or the other. That's the classic two-tailed test. So for a two-tailed test, we have a research hypothesis and we have a null hypothesis. And this is going to help us out more so when we're doing our one-tailed test. But let me just set it up right now. So we got two-tailed over here. We got one-tailed over here. And we have three possible outcomes of any experiment, any treatment. There's three things that can happen. Number one, your treated population might be lower than your untreated population. Your treatment causes a decrease, right? That's possibility number one. Whatever you're doing causes a decrease. Possibility number two is that whatever you're doing causes an increase, right? So whatever your treatment is, it causes an increase in the scores. And then the final possibility is that your treatment does nothing, right? So whatever the mean was before the treatment is going to be the same after the treatment. Your treatment doesn't actually do anything. Your hypotheses have to cover all three situations. Every statistical analysis has to choose or be able to choose between one of those three. So when we are doing our research hypothesis for a two-tailed test, we say that the treatment does have an effect, and we write, when we're doing the research hypothesis, we say that the treatment does have an effect. When we're doing the null hypothesis, we say that the treatment has no effect. The research and the null hypothesis will always be complete opposites of each other. Research hypothesis, treatment has an effect. Null hypothesis, treatment has no effect. One of those two has to be true. Either your treatment does something or your treatment doesn't do anything. There's no other option. One of those has to be true. The research hypothesis, we write that out as the mean of your treated population does not equal the mean of your untreated population. So that is a two-tailed test, that the mean of your treated population does not equal the mean of your untreated population. And that is covering a decrease because of your treatment, and it's covering an increase, right? Because if it decreases, then it's not equal. And if it increases, then it's not equal. So that one statement, the treated population is not equal to the untreated population, covers both decreases and increases. And then the null hypothesis, that the mean of the treated population equals the mean of the untreated population, that covers the final possibility. And you can see in a two-tailed hypothesis, we got everything covered, right? We have all three possibilities covered, and that's how you know you've done a correct set of hypotheses. All right, so that's two-tailed. We've seen those before. What about one-tailed? What happens in a one-tailed question? Well, in a one-tailed question, we're no longer interested in whether or not there's just a difference. Now we're interested in this particular direction. So let's say that we wanted to know whether or not our treatment causes an increase, right? So for example, one example where we've already seen where this directional hypothesis makes sense is in that games program for the students in that elementary school where we're trying to increase their self-esteem, right? We are only interested in an increase. We're only interested if our treatment causes an increase. We don't care, or we're not interested at all, if our treatment causes soul-crushing losses in self-esteem. That's not what we're trying to accomplish. So in this case, we would only want an increase. For a one-tailed hypothesis test, the research hypothesis is by far the easier one to get. So do the research hypothesis first. The treatment causes an increase. The null hypothesis has to be the complete opposite of that. And the complete opposite of causes an increase is that your treatment does not cause an increase, right? Your treatment does not increase the scores. So treatment causes an increase, research hypothesis. Treatment does not cause an increase. That's your null hypothesis. Exact opposite of each other's. In this case, the research hypothesis will be that your treated mean is greater than your untreated mean. Your treated population is greater than, the scores of your treated population are greater than the scores of your untreated population. That covers this possibility right here. All right, so that covers that possibility right there. The null hypothesis has to cover everything else. So the null hypothesis here is that the treatment does not cause an increase, And that is written as your treatment is less than or equal to your untreated population mean. So that covers the less than, which we're not interested in, which is right there, or equal to, which is right there. Once again, covers all three possibilities. Some places you might see the null hypothesis written as equals. In your textbook, I believe sometimes in the homework it's written as equals. I might be wrong on that, I hope I am. But it needs to cover all three possibilities. The correct null hypothesis for a one-tailed hypothesis test is that your treatment does not cause an increase. In this case, your treatment is less than or equal to the original population. And again, that covers all three possibilities. So that's one version of the one-tailed hypothesis test. That's for when you're looking for an increase. Did we increase self-esteem? Did we increase learning outcomes? Sometimes you're interested in the opposite effect. You want to know, did your treatment cause a decrease? This is usually the case for any problematic behaviors. Did we decrease depression levels? Did our treatment decrease OCD behaviors, obsessive compulsive disorder behaviors? Did our treatment decrease distractibility? Did our treatment decrease social anxiety, right? So there are a lot of behaviors that we want to decrease. We would test with a one-directional, one-tailed hypothesis. So if that's the case, the treatment causes a decrease, that's your research hypothesis, that's what you're looking for. The null hypothesis, complete opposite. Your treatment does not cause a decrease. And in this case, we have now the research hypothesis being that the mean of the treated population is less than the mean of the untreated population. So we have the mean of the treated population being less than the untreated. Right? So we have now this possibility being covered by the research hypothesis. The null hypothesis has to cover everything else. So it is the complete opposite. So the mean of the research hypothesis, the mean of the treated population is less than the mean of the untreated population. Null hypothesis, complete opposite. Mean of the treated is greater than or equal to the mean of the untreated population. Covers greater than, covers equals to, covers all three possibilities. You have a full hypothesis test. All right, any questions on that? Okay, so we're going to take a break right now, and when we come back, we're going to revisit the elementary school example where we were taking a look at the effect of a games program on self-esteem, because we were originally doing it with a two-tailed hypothesis test, and we're going to see that that was actually the incorrect test because we're not interested in decreases in self-esteem. We're only wondering, does our experiment, does our treatment increase the self-esteem of these students? So it's 10:06. Let's take just a quick 10-minute break so we make sure we got practice time today. We'll come back in 10 minutes, so 10:17. Let's reconvene, and feel free to take a break. And if anybody has any questions about anything they've seen, feel free to call me over.